So what are the sort of techniques that we commonly find in downstream processing? Liquid-liquid extraction is a very common one. It's often used to separate organic products from inorganic byproducts. It's a common technique used to isolate products from high boiling dipolar aprotic solvents. Involves partitioning between usually an aqueous and an organic solvent phase, although occasionally you do get immiscible organic phases. Typically, additives like acids and bases may be added to increase aqueous solubility. So if we can form a salt, take it into water, wash it with a solvent, neutralize and recover by washing with another solvent. It's fairly typical. Additives like inorganic salts may be added to improve phase separation and reduce emulsions. Sort of the drawbacks are that multiple extractions might be required. And in liquid-liquid extraction, we often generate multi-component waste streams. As we saw with that lotrifibane example, it always needs to be borne in mind that a reaction done in water and extracted with an organic solvent is no greener than a reaction done in organic solvent and washed with water. Isolation of solids, again, a very, very common way of isolating and purifying intermediates and final product, APIs. Solids, we can form them via crystallization or precipitation, which is just a very fast precipitation, often giving us amorphous materials. It can be a very efficient way to isolate product and purge impurities. If we think about designing a crystallization, we should, if possible, avoid excessive solvent use washing, try and avoid very low concentrations. Solvent swapping to go from a reaction medium to a crystallization precipitation solvent is resource intensive. The most efficient way of doing this is the so-called direct drop, where reagents and starting materials are soluble in a hot solvent, but the product will crystallize efficiently when the reaction mixture is cooled. Now, it's not always possible to do that, of course. Maybe the next best option is to add an anti-solvent direct to the reaction mixture to crystallize the product out. The addition of anti-solvents, of course, for crystallizing and precipitation will always reduce volume productivity, and that's got to be borne in mind. Distillation, this is another technique used to separate and isolate products. Maybe not so widely used in pharmaceutical manufacture, especially later on in the synthetic sequences. Most intermediates and products are just not volatile, but can be useful for low molecular weight intermediates early in the synthesis. So distillation, we can separate mixtures, purify, isolate products, reduce volumes of solvents in processes, and this is probably fairly common use for distillation in the pharma industry, and of course solvent recycling. So generally, as a purification technique, distillation through packed fractionation columns is not widely used, as we said, as many APIs and intermediates are non-volatile, but possibly is used for in early stage intermediates, low molecular weight materials. We can use distillation techniques like short path or white film distillation if the products are particularly heat sensitive. Probably the most common use of distillation in pharma synthesis is to reduce solvent volume or in solvent exchanges in work up DSP operations and for solvent recovery. Distillation can be a high energy process, and solvents at the higher and lower end of the boiling range, so it's very high temperature, temperature needed to distill solvents, or very high vacuum cryogenic condensing requirements for very low boiling point solvents can be energy intensive, and we always need to bear this in mind. Filtration and drying, again, most intermediates and final products are isolated as solids. This is a very common set of unit operations. So these can be intensive in terms of plant time utilization and energy. So we need to bear in mind the final API will have very specific solid characteristics which will need to be adhered to and replicated. Specific solvent levels as given in regulatory guidelines will also have to be achieved. So obviously drying is very important here. Generally for intermediates, we need to try and design processes and crystallizations that give easy to filter and wash materials. So that's avoiding low bulk density fibrous materials. High boiling solvents, as we mentioned earlier, these can be difficult and very intensive to remove. So a high energy requirement in distillation and high energy requirements in drying. If you have a material or intermediate, does it need to be isolated? And we'll talk a bit more about telescoping reactions later. Maybe we don't need to actually isolate that particular intermediate. If the material needs to be filtered and washed to remove impurities, does it need to be dried before the next reaction? So, if there's a few percent of a solvent there, or water, and it's going into the same solvent or a compatible solvent, do you really need to spend time and energy drying it? We always need to be aware that in the cGMP stages, a number of points of control or isolation points and analysis points are generally required to ensure quality of the final product. And there's a reference there that's worth looking at. Chromatography, this is very widely used in medchem and in the early stages of synthesis. Certainly in the first few hundred mgs or grams, most products are purified by chromatography. And indeed, if we look at scale up, we can still find various forms of chromatography used there. So simulated moving bed, SMB, and supercritical CO2 can be scaled, and at large scale they can be equipped with automatic solvent recovery and recycle, thus minimising impact. These techniques, however, are really best applicable to the separation of binary mixtures like enantiomers, rather than the isolation of a product from a complex matrix of impurities. Normal and reverse phase chromatography are better suited to this task, and are certainly often employed in the early stages of development to quickly provide supplies of a pure API. And indeed, these techniques can be scaled. But they do generate large amounts of solvent or solvent aqueous waste to deal with, and eventually you'll have to dispose of the spent stationary phases. So these techniques may be the best technology for the purification and isolation of very low volume, high value materials, but in most cases, alternative techniques for isolation and purification will give better sustainability metrics. Now, as in the bond forming steps, there's always new technologies being investigated and being brought on stream. Continuous processing, of course, is a topic of current high interest. There are a number of techniques widely used in other industries that are being investigated for use in pharma, really to provide more efficient and sustainable DSP and isolation technologies for APIs and intermediates. Membranes, both ceramic and polymeric nanofiltration membranes, are being investigated for a range of tasks. So separation of impurities based on molecular weight, catalyst separation and recycle, and for swapping a high boiling solvent for a low boiling solvent, which is actually quite difficult to do via distillation. Liquid extraction, so we can move to continuous processing there, especially when we have very high volumes of liquids to process. And currently a very big topic is looking at moving to continuous separation and crystallization, and there are certainly a number of innovative reactor designs under evaluation for the continuous crystallization of APIs and intermediates.